Hello and welcome to this tutorial on classifying sea ice and leads using AI. In this brief overview, we'll walk through the essential steps for pre-processing satellite data and building a machine learning classification pipeline, all within Google Colab. Colab is really good because it offers free GPU resources and there's nothing to install on your computer. You just need a browser and a Google account. So first you'll want to download the Week 2 folder from the course resources provided on the middle page. After unzipping it, upload the contents to a folder in your own Google Drive, then open the Sea Ice and Lead Classification Jupyter Notebook in Colab. Be sure to connect your session by clicking the Connect button in the top right corner and then mount your Google Drive. When prompted, grant the required permissions. Next, we import the necessary packages like NumPy and Matplotlib. Make sure to change any file paths to match the location of your own Week 2 folder. To do that, locate the Sea Ice and Lead Classification Notebook in Drive. Click on the three dots and copy the path. Paste that path into the code cell where we defined our main data path. After that, you'll notice we specified the region of interest using coordinates that line up with the mask we created in Iris. In this example, x1, y1, x2, and y2 are set to 100, 700, 300, and 1000, but you'll want to use coordinates that match your own Iris mask. Once you run these cells, the notebook will extract the correct section of the satellite image and display it. Pay attention to the part where we create 3x3 patches. This ensures that every pixel is labeled not just in its own value, but also in the context of its 8 neighbors. Because our data has 21 bands, each 3x3 patch holds quite a bit of information. Also keep in mind that border pixels can't form a full 3x3 patch, so they get excluded. We then balance our data set so that both classes, sea ice and lead, appear roughly equally. Finally, we save the train and test arrays for the next notebook. Now you'll want to open the AI/machine learning implementation notebook. This is where we load back in our xtrain, xtest, ytrain, and ytest arrays. Again, watch out for file paths and adjust them to your setup. We have a few classification approaches here. Convolutional neural networks, aka CNNs, are ideal for images because it uses convolutional layers to detect spatial patterns, like edges and textures at different scales. In our code, using TensorFlow, we define a convolutional layer, a pooling layer to reduce spatial dimensions, and one or more dense layers for the final classification. CNNs can sometimes offer higher accuracy because they learn hierarchical features, but they can also be more computationally intensive. Random forests train multiple decision trees on bootstrapped samples of the data, then aggregate the predictions for a final result. This approach is often faster to train than deep networks and can handle tabular or structured data well, but it might not capture the full image context as effectively as a CNN does. So our code basically reshapes each 3x3 patch into a single row and feeds it into a random forest classifier from scikit-learn. Finally, vision transformers, also known as VITs, are a more recent innovation in deep learning. They rely on self-attention instead of convolution, so they split the input image into patches and process them through transformer blocks like those used in NLP models. VIPs can achieve some really impressive results on image tasks, especially with large datasets, but they're more complex to set up and are quite data hungry. So we usually use TensorFlow or PyTorch for implementing this. So you can see that in our notebook, it shows the essential structure. So after trying and experimenting with these methods, you might find that CNNs often strike a good balance of accuracy and training time, while random forests are quick to implement and can be sufficient for many tasks. And VITs may outperform the others if you have enough data and computational resources, but they can be slow to train and trickier to configure. Lastly, we talk a bit about cross-validation and model selection. Underfitting, overfitting, and the proper use of validation set or k-fold approach are all key to ensuring our model generalizes well. So you'll see in the example code that performs a grid search over the different hyperparameters. This helps us systematically find the best setting for our classification tasks. So for instance, we can tune the number of estimators in a random forest or adjust the number of layers and filters in a CNN. These are all essential in balancing performance and efficiency based on your project's needs. After completing these steps, you should be able to build a straightforward sea ice versus lead classifier and experiment with 3 different approaches: CNN, random forest, and visual transformers. You can fine-tune the parameters again and or bring in your own data if you like. So I hope this tutorial has been useful in introducing you to AI-driven sea ice classification. Best of luck in your experiments, and thank you so much for watching.